Hello everyone, my name is Dr. KCH Apparao, working as an associate professor in mechanical engineering department. Today I would like to explain on critical thinking questions on question bank which are given in the question bank. In this class we will see derivation of LMTD method for parallel flow. Okay, so these are the questions which are given in the question bank. Derive an expression for LMTD in case of parallel flow, double pipe heat exchanger. So a few more questions. We'll see first of all, what is the importance of LMTD? LMTD is the method to design parallel flow heat exchanger or counter flow heat exchanger, any heat exchanger. You know this, if you take any homogeneous body, the temperature is T1. Temperature is T2. Thickness is equal to L, area is equal to A. In this condition, the formula for heat transfer rate of heat transfer Q is equal to Ka into delta T by L. For conduction, this is the conduction formula. We know that for convection, Ha into delta T. If you consider more number of layers, then the formula is equal to UA into delta T. Okay. So delta T is the temperature difference. Hot fluid, there are only two fluids. Heat exchange takes place only two fluids. We study in heat transfer from between only two fluids. Okay, so hot fluid minus cool fluid, you know this one. But in case of heat exchangers, the temperature transfer from hot fluid to cool fluid is varies from point to point. Suppose we are taking the one pipe and envelope is there. Okay, so we are considering here parallel flow heat exchanger, hot fluid inlet, hot fluid outlet, cool fluid inlet and cool fluid outlet. Okay, so heat transfer takes place between two fluids, hot fluid and cold fluid. Both the fluids parallel to each other and in the same direction. That shows the parallel flow heat exchanger. If you see the temperature graph for this one, okay. This is the hot fluid entering, this one is the cold fluid entering. Okay. So the hot fluid temperature gradually decreases, TH0. The cool fluid temperature gradually increases, TC0. Okay. So in this condition, the temperature of the cold fluid varies. The transfer or heat transfer from hot fluid to cold fluid. So in this, the cold fluid temperature is gradually increases from point to point. Similarly, hot fluid temperature gradually decreases from point to point. It means we know that the temperature difference between the hot and cold fluid in heat exchanger varies from point to point here, not fixed. So not fixed. Here, in the case of homogeneous bodies, the temperature is fixed, T1 and T2. But here temperature changes. Temperature difference between the hot and cold fluid, it changes from point to point. So to calculate this one, we use the logarithmic mean temperature difference. We use logs. Okay, so that is the logarithmic mean temperature difference. By using logarithmic mean temperature, we will find out the delta TLM. Delta TLM temperature difference with respect to LMTD method. then the formula rate of heat transfer P is equal to UA into delta T LM. So we have to find out delta T LM with respect to LMTD. Okay. So because of this reason, because the temperature difference between hot fluid and cool fluid varies from point to point. So to find out the general equation, we have to consider the logarithmic principles. Okay. This is the reason. Therefore, based on the concept of appropriate mean temperature difference, that is nothing but logarithmic mean temperature, we will find out the total heat transfer rate in the heat exchanger. Okay. So now we'll see how to find delta Tm in parallel heat exchanger. We'll see this one. This one is the already given formulas. So what I already explained here, then you can refer this one. Just okay. You know that Q is equal to UA overall heat transfer coefficient into, because there are many there are different surfaces, hot fluid inner surface, hot fluid outer surface, cold fluid inner surface, cold fluid outer surface. So in each case we have to consider the heat transfer rate, then we have to find out the overall heat transfer rate. Then the formula is Q is equal to UA delta T LM. AU is the overall heat transfer coefficient, watt per meter square Kelvin. Area, A is equal to area. Delta TLM, that is nothing but logarithmic mean temperature difference. We will find out how to find. We will solve how to find the, or we will see how to find the temperature difference delta TLM. Okay. So, LMTD method for heat exchanger. The variables or the variable analysis of any heat exchanger that involves mainly inlet and outlet temperatures. Inlet temperature of hot fluid and cold fluid, and outlet temperature of hot fluid and cold fluid. Next, overall heat transfer coefficient. Overall heat transfer coefficient. So next one is the total surface resistance and total heat transfer rate. So these are the important parameters which are included in LMTD method. Okay, we know that since hot fluid is transferring heat or a part of its energy in the form of heat to cold fluid, so there will be an increase in enthalpy of the cold fluid and corresponding decrease in enthalpy of the hot fluid, because heat transfer takes place from hot fluid to cold fluid. So enthalpy of hot fluid decreases and enthalpy of cold fluid will be increasing. Okay, so the formulas, you know this one. Q is equal to, for hot fluid, MHCH into THI minus TH naught. Hot fluid temperature difference, hot fluid inlet minus hot fluid outlet. Okay, so MHCH, specific mass and specific heat. So mass of hot fluid. So you can write like this one, capital CH into THI minus TH naught. Capital CH is the specific heat of the hot fluid. You know this one. Okay. Similarly, for cold fluid, CC into TC naught minus TC. Okay. We denote the difference between hot fluid and cold fluid, that is delta T, temperature difference, hot fluid minus cold fluid temperature. Hot fluid temperature minus cold fluid temperature. Then the formula is equal to UA delta TLM. We will derive this UA delta TLM. Okay, rate of heat transfer. So here we will see cold fluid heat transfer, heat exchanger. This is the pattern of cold fluid heat exchanger. Hot fluid and cold fluid enters at one side. Hot fluid and cold fluid leaves on other side. So hot fluid inlet here. Here also cold fluid inlet. Okay. So these are the hot fluid outlet and cold fluid outlets. The temperature profile is like this one. You know this one. Just I am drawing again. So this is the hot fluid inlet. This one is the cold fluid inlet. Okay. So cold fluid because heat transfer takes place from hot fluid to cold fluid. So hot fluid temperature gradually decreases. TH naught. So heat takes from hot fluid. So because cold fluid takes the hot heat from hot fluid, so hot fluid temperature gradually increases. So this is Tc naught. Okay, we can represent this one. This is the delta T1. We can represent this is the delta T2. Delta T1 is nothing but inlet temperature hot fluid minus inlet temperature of cold fluid. Similarly, delta T2 outlet temperature differences. Okay. So here for finding derivation, so we will take small elemental area dx. So this is the small elemental area dx from x distance. Okay. We will derive the rate of heat transfer for this small elemental area. Then we can understand, then we can integrate with respect to limits. What is the limits? Delta T1 to delta T2 limits. Then we will get to overall heat transfer coefficient. Okay. So first we will solve the heat transfer rate of heat transfer dq for this small elemental area. Okay. So here we can see delta T is nothing but dTh minus dTc. First of all, we have to find out the small elemental area, that is dq is equal to u dt into elemental area. Okay, so u dA dt. This dt is nothing but th minus tc. You will see derivation here. Okay, for this small elemental area. So before going to derive this one, we'll take some assumptions also. Those assumptions are U overall heat transfer coefficient is uniform throughout the heat exchanger, so it will not be changed. Next, potential energies and kinetic energy changes are negligible. We are not considering these energy changes. Okay. Next, specific heats, hot fluid specific heat and cold fluid specific heats of the fluids are constants, not varying parameters. So throughout this process, we will consider these as constants. Okay. Next, heat exchange takes place only two fluids. We are considering heat exchange between only two fluids. Next, temperatures of both fluids are constants. So it means inlet temperature and outlet temperature of hot fluid, cold fluid inlet, cold fluid outlet. So these are the fixed one. It will not be changed. So these are the assumptions to find out the LMTD method for parallel fluid heat exchanger. Okay. First of all, we'll take heat transfer between hot and cold fluid for a small elemental area. Small elemental area, that is nothing but dx. Okay. For the small elemental area, then dq derivative, because q is the overall. So dq is the rate of heat transfer for this small elemental area. dq is equal to u dA into dt, delta t. dt is nothing but hot fluid temperature difference, u dA into hot fluid temperature minus cold fluid temperature. Okay. So these are the formulas. But we know the, so here we can observe here. Okay. So they are the graph for the cold fluid temperature, parallel fluid heat exchanger. This is the delta T1, this one is the delta T2, this is the delta T. Delta T is the nothing but TH minus TC. Okay. Now we'll see energy balance over the hot and cold fluids for this small elemental area. Okay, small elemental area energy. We know that overall energy balance equations Q is equal to MACH into TH minus TC. TH naught. So temperature difference of hot fluid and temperature difference of cold fluid. But here we are considering first energy balance over a hot and cold fluids. We are taking for this small elemental area dq is equal to mass of hot fluid into CH into DTH. Okay. So we can read it like this one, minus capital CH, specific heat of the hot fluid into TH, DTH. Okay. So for this small elemental area. Okay. So here we are using minus because heat is gradually decreasing order. For the hot fluid, heat profile is gradually decreasing order, but cold fluid is gradually increasing order. For this one, you can take dq is equal to minus, so capital CH into DTH. Okay. Similarly, dq for cold fluid, but is a gradual increasing profile, so capital CC into DTC. Okay, we have to remember these formulas. Then we can rewrite like this one, like because so from this one we can write like this one, DTH is equal to dq by minus CH. Similarly, DTC is equal to dq by CC. So from this formulas we can rewrite like this one. Okay. We know that temperature difference delta T is equal to hot fluid temperature minus cold fluid temperature. If you derivative in both directions, both sides, so derivative of delta T, this is the derivative of TH, this is the derivative of TC. Okay, so these are DTH minus DTC, nothing but DTH minus DTC. Here we can take these values instead of DTH and DTC. Okay, then derivative of delta T is equal to minus dq by CH minus dq by CC. Okay, so in both condition minus is there, you can take minus dq is the common term. Then 1 by CH plus 1 by CC. Okay, so similarly here we can see derivative of delta T is equal to minus dq into 1 by CH plus 1 by CC. Okay, so you know that dq is the formula for this small elemental area, U dA into dt. U dA into dt. You can substitute this value, this term here. So minus U dA into dt. Okay. So here delta T, here also dt. You can bring that term to left side. Then the equation will be like this one. Derivative of delta T by delta T. So temperature profiles here minus U into 1 by CH and 1 by CC. According to assumptions, all these are constants. Overall heat transfer coefficient is constant for the entire heat transfer in the heat exchange. Then CC and CH also we are assuming these are the constant parameter. Then variable parameter is the dA. So we can integrate both sides. Integration here limits is equal to, so you know that the temperature profile is hot fluid inlet, hot fluid outlet. No, this is the cold fluid inlet, cold fluid outlet, hot fluid outlet. Okay, so this is delta T1, this one is the delta T2. Area, this is 1 to or 0 to 1 or 1 to 2. You can take. Okay, area is uniform. So overall area you can take, that is A. Okay, so we are taking the limits delta T1 to delta T2. Here area 1 to section 1 to 2. Here area is common, that is integral of dA is nothing but A. Okay, so here derivative of delta T by 1 by T. So that is the value is equal to this one, log of delta T2 by delta T1, because log of 1 by delta t. If you substitute the limits, then we will get to this one, ln delta t2 by delta t1, or delta t2 minus delta t1. You can rewrite like this one, ln into delta t2 by delta t1. Next, integral of dA is nothing but area. So then the formula will be like this one, minus UA into 1 plus CH plus 1 by CC. So this is the equation for the small elemental area. But you know the energy equation according to thermodynamic principles, that is nothing but for with respect to hot fluid and with respect to cold fluid, overall heat transfer coefficient Q is equal to mHCH into hot fluid temperature differences THA minus TH0. So mHCH is nothing but capital CH, specific heat of the hot fluid, into temperature difference, hot fluid inlet minus hot fluid outlet. Then you can rewrite this formula like this one, 1 by CH, because we require the 1 by CH. So 1 by CH is equal to THA minus TH0 by Q. Similarly, for cold fluid, MCCC nothing but capital CC, specific heat of the cold fluid, TC0 minus TCA. Okay, so 1 by CC is equal to TC0 minus TCA, the temperature difference of the cold fluid by heat transfer coefficient. Then you can substitute these values in this equation. You know that 1 by CH value, 1 by CC values also. Okay, if you substitute these values here, then you will get this formula. Here in left side, ln delta t2 by delta t1 minus UA into 1 by CH is nothing but THA minus TH0 by Q here. Okay, so Q is the common term. Similarly, 1 by CC is nothing but TC0 minus TCA by Q. So Q is common here and here, you can take common that one. Okay, then remaining is 1 by CH, 1 by TI, 1 by hot fluid inlet minus hot fluid outlet, cold fluid outlet minus cold fluid inlet. Okay, so these temperatures, we can convert these temperatures into this delta T values, because you know this one, delta T1 is equal to hot fluid inlet minus cold fluid inlet one side, because already you profile, you know that profile, hot fluid inlet decreases, hot fluid outlet, cold fluid inlet increases, cold fluid outlet. So this is delta T1, this one is the delta T2. Okay, so delta T1 is equal to THA minus TCA, delta T2 is equal to TC0 minus TCA, because C0 value is greater than outlet temperature of cold fluid is greater than the inlet temperature of the cold fluid. Okay, so we can rearrange this temperatures. It means THI minus TCA. So first bring this term near to inlet temperature of hot fluid. Then you can take common, minus is the common. Then TH0 minus TC0. Okay, so the equation will be like this one. So we rearranged this temperatures of the hot fluid and cold fluid. So then you know this one, hot fluid inlet minus cold fluid inlet, that is nothing but delta T1. Hot fluid outlet minus cold fluid outlet, this is nothing but delta T2. Then the formula is like this one, ln delta T2 by delta T1 is equal to minus UA by Q into delta T1 minus delta T2. Okay, but here minus is there, because of minus just we can rearrange this terms, UA by Q. If you send the minus in bracket, so into the in bracket, then so delta T2 minus delta T1, then the final formula Q is equal to rate of heat transfer is equal to UA, overall heat transfer coefficient, into area into delta T2 minus delta T1 by ln delta T2 by delta T1. So this is nothing but delta ln Lm. So delta Lm is equal to delta T2 minus delta T1 by ln of delta T2 by delta T1. Okay. So otherwise you can write like this one also, delta T1 minus delta T2 by just by ln delta T1 by delta T2. You can write like this one also. Okay. So this is nothing but Q is equal to rate of heat transfer is equal to UA into delta TLM. Okay. For heat exchangers, we use this formula delta TLM, logarithmic mean, because temperature varies. But in case of homogeneous body and cylindrical objects, we will take directly UA into delta T, temperature difference. Okay. So this is the formula for the rate of heat transfer in parallel flow heat exchanger by using the LMTD method. Okay. This is the derivation. So this is the one numerical. We can see this one. So okay. So this one we'll see in next class. I would like to explain this one. Okay. These are the different textbooks for the reference. You can refer this one to understand the concept of LMTD, method of parallel flow heat exchanger. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.